Diffraction. Diffraction is the bending of a wave as it passes through a small opening or around a barrier. This phenomenon substantiates or supports the wave nature of light. Now, I have the word small here in quotation marks. The smaller, or the relative smallness of the opening, the greater the diffraction. Diffraction is a little bit like refraction in a sense because it's bending, but as you remember, refraction is the bending of a wave, any wave, as it enters a new medium. Diffraction, the wave stays in its present medium, but it goes through a small barrier or through a small opening or around a barrier. I'll show you some examples with actual water waves in class. These 5 examples right here are overhead views of, say, water waves in a tank going through or around, through an opening or around a barrier. But let's talk about this relative smallness. For example here, the most pronounced diffraction that we have in these 5 pictures, this one is fairly pronounced diffraction. The plane waves are traveling this way, flat waves, straight waves, traveling through a barrier, and there's this really tiny opening, and the opening is tiny. So the smaller the opening, the more the bending. When the wave goes through that opening, it bends and becomes circular waves on the other side, which is counterintuitive. You would think that the waves would just, a little piece of the wave would get through, but actually the waves get through and it forms circular waves on the other side, and they expand after they get through that opening. This over here also shows fairly significant diffraction. Even though it's a larger opening, the wavelengths were bigger. So once again, you can make the opening look small, either physically it is small, like in the middle diagram, or it looks smaller to bigger waves, like it is in the right-hand diagram. In the first diagram over here, on the left, not much diffraction because we have small waves going through a big opening. There's a slight diffraction there, slight bending, but not a whole lot of pronounced diffraction there because the opening is big. You need a small opening, relatively speaking, to the wavelength of the wave to get significant diffraction. Same thing with these barriers down here at the bottom. There's more pronounced diffraction here on the left diagram because the waves are big. The bigger the waves, the smaller the barrier tends to look, so to speak, and you get more pronounced diffraction. Huygens principle is essentially a precursor to diffraction because it sort of explains diffraction. It explains how waves propagate and diffract. And it says that every point on a wavefront serves as a source of secondary waves. So what's happening here in this diagram, you have these wavefronts, these circular wavefronts in blue. I'll highlight them. And what's happening is what they're showing you here is these wavefronts are traveling outward from the original source S. But what you do here is if you take any point on the first wavefront, A, B, that curved semicircle, and you take any point on there and draw a circle around those points, you get little wavelets. So each of those little circles over here, now it's not showing them really coinciding too well. Well, this right here might match up with that first point. So all these little arcs here that I'm drawing are called wavelets. They're circular wavefronts. That would be centered around the red dots that I drew on the wavefront AB. And if you keep drawing these little wavelets, they define that second wavefront, CD. That's Huygens Principle. I could do that all day long. I could draw millions of points on that first wavefront, and then you would do the same thing for the next one. Actually, let me do that. If I draw a bunch of locations on wavefront CD, and then did the same thing again, drew little wavelets centered on those ones I just drew on CD, once again, these wavelets would define the next wavefront. I'll draw that in blue. So then we'd have another wavefront over here. I could call that EF. It's showing that the wave is traveling outward. Revisiting wave interference once again, and all these things we're talking about here in these notes apply to all waves, water waves, light waves, sound waves. We'll apply it mostly to light waves, but they apply to all waves. So you have the constructive interference. If you have two interfering waves that are, in this first case, constructive, they're in phase. These two waves are in phase. So when you add together, the resultant wave is basically the summation, algebraic summation, and a wave that's, if the two initial waves were the same size as each other, same amplitude, the resulting wave would have twice the amplitude of either one of the initial waves added together. If you have destructive interference, right, the two waves are out of phase. Typically, we would say they're 180 degrees out of phase, because 180 degrees is half a wave, half a circle. If they're 360 degrees out of phase, they're not really out of phase. They'd be back in phase because you'd have coincidence again, because a full circle brings you back into phase with what you had initially. But if you're 180 degrees out of phase, you're completely opposite of the other wave. You add those together, you get nothing. If it were sound waves, you would get quietness. If they were light waves, you'd get cancellation, you'd get darkness, and so on and so forth. Back in 1801, a gentleman by the name of Thomas Young did a pretty famous experiment called the double slit experiment to measure the wavelength of light. And this incorporates diffraction and interference to really explain this experiment. Now, we're not going to get into the math of this year, but bottom line is you have a source of light way over here on the left-hand side, goes through an opening, you have some diffraction here to begin with, but then you have these two slits, S1 and S2, where the light goes through there, those two spots, and once again you get two waves that now come through there and are interfering with each other, and you get constructive and destructive interference in a pattern. You get an interference pattern. Dead center, what always happens here is along this line right here, you get maximum. If it's light, you get a bright light, and on this diagram on the far right here, this is really, really bright in that central region there. And you can see in the actual notes it's also bright, because you have like a crest meeting a crest for two waves that are interfering. They're in phase with each other right there. As opposed to, and I'll use a darker color here, along this region right here, you essentially have the crest of one wave matching the trough of another wave, so they're out of phase 180 degrees, so that is a minimum, and you get darkness. Same thing is true just to the right of that. It's symmetrical. You get minimum, you get cancellation, and you get dark. So the pattern, the interference pattern, is a band of bright and dark spots, because once again, after the destructive interference, there are locations where crest meets crest meets crest along that region right there, and over here, and so on and so forth. That gives you another maximum. That gives you brightness there and brightness there. And you can see the pattern repeating. For those students lucky enough to take AP Physics next year, we'll explain the mathematics of this. All you need to know is that this year is that Young did an experiment using slits, double slits. The light passes through the slits, it diffracts, it bends, and then the two waves of light through those two different slits interfere with each other constructively and destructively to result in a pattern of bright and dark spots because of the interference. Thin film interference also is kind of fun to deal with. Let me just kind of do this backwards. It's responsible for the colors, the iridescent colors you see in soap bubbles. Or the bubbles you played with when you were a kid and you blew them into the air. You see colors in them, but they're kind of interesting. What you'll see primarily in those soap bubbles is cyan, magenta, and yellow. Those colors should sound familiar. Red, green, and blue. Those are the 6 colors that you'll primarily see in those soap bubbles, because the cyan, magenta, and yellow parts of a soap bubble really kind of coincide with how thick the soap bubble is at those particular levels or areas. And what it indicates is, like when you see yellow in a soap bubble, what's happening is that's red and green light to your eyes. What's happening is the blue light is getting destructively interfered with. It's been taken out. So if you take out blue, you end up with red and green to your eyes. You see yellow. Conversely, where the cyan part of the bubble is, you're seeing blue and green. You've lost the red. The red is destructively interfered with. It's out of phase with itself. The red light cancels itself out. And then the magenta part of a bubble is where the green has canceled out. Similar things happen with oil on a wet road. You see those very same colors. Or in peacock feathers and other animals, there's some of this going on. This colors by iridescence, because what's happening is either there's some constructive interference for some colors or destructive interference for other colors, because what happens is the light is going in to this film, okay? Some of it reflects off the surface, some goes into the film, refracts, bends when it goes in, reflects off the bottom or another surface at the back end, comes back out, and these two beams 1 and 2 interfere either constructively or destructively. Like I said before, like in a soap bubble, if beams numbers 1 and 2 for that particular thickness matching up with the wavelength of blue, and once again next year we'll get into the actual specific math of this if you take AP Physics. If the blue light is destructively interfered with because of that particular path, and those two waves would be out of phase for blue, you'd end up with basically seeing yellow, which is red and green, in that part of the soap bubble, because of the thickness of the bubble in that case would cancel out the blue light. And the same thing happens with oil on a watery surface. Sometimes you've seen this after rainstorms and so forth. Peacock feathers, the same thing, same idea that's responsible for the colors you see in these particular situations. But the only thing that you need to remember then is that the colors are a result of either constructive or destructive interference. Incoherent versus coherent light. Incoherent light is light of mixed colors and various phases. This is the typical kind of light you would get from a light bulb or a fire or from the sun. It's basically light of all different colors mixed together. Red, orange, yellow, green, blue, indigo, violet, mixed together. Coherent light is a specialized light. It's light of one wavelength, one color, one frequency, all in phase. The best example of coherent light is laser light. Now the acronym LASER stands for light amplification by stimulated emission of radiation. Don't be scared, it's not dangerous radiation, well, unless you stare into it. It's, we've all had or seen lasers, played with lasers. They're used in DVD players and so forth. But it's light, specialized light. It's all light of one. You can see the diagram here. It's light of one color. It's monochromatic, by the way. You can pretty much guess what that means. Mono means one, and chromatic means color. It's one color. So laser light is coherent light. It's monochromatic light. By definition, you can have a green laser or a red laser or a blue laser, and you can then mix those colors. But each laser by itself is only one color. All that light's in phase, as you can see in the diagram here, all matched up. So it stays together in a nice tight beam typically, and it has a lot of good uses, like I say, DVD players or in medical applications and pointers and so forth, because it's coherent, it sticks together, and it has these unique properties.